University at Minch, Ethiopia. So he's going to give us his presentation focusing on experience of fecal surgical management at Minch. So welcome, thank you very much. I'm afraid if I come and stand next to you and look intimidating, making a subtle hint that I want you to finish. Thank you.
Good afternoon, everybody. I'll try to rush. My presentation is on the experience of fecal surgical management in a small town from Arnhem, southern Ethiopia. And my outline will be as follows. And in the town, the main toilets are pit latrines, and the ground structure or the soil structure of the town is rocky and fragile soil. Because of that, most of the toilets are shallow. And because of the soil texture and no pit lining, it is a mix of solid waste and soil. This is the finding of a baseline study on Rosa 2007. 10% of the population of defecate, and about 64% they squat on wood toilet. The toilet is not of substandard. These are the toilets, most of the toilets. You see the floor is made of wood, and they have grass cover. Privacy cover, and sometimes you can have sheets cover, and sometimes there is no privacy cover. And this is for school toilets, and there is also VIPs, and recently, this is 2007, because our toilets are flourishing because of the loan from. So Desludging is number one with truck, and it is dislodged or it is thrown away in an isolated in the nearby town. However, because of the low load and changing of the disposal site, it is dried like this, so there is a possibility of disinfection. There is also reuse. Also, it is illegal. They are breaking the sewer line, untreated sewer line, and they reuse it. And there is also disposal in the farm. Of course, the farmers usually pay. And for EcoSan toilets, there is a cart transport like this. These are organized use groups. What I'm emphasizing is the importance of manual dislodgers. These people are often isolated, and they are generally come from low-income communities. And what they are doing, this is important, which I emphasize. I followed from 11 in the evening to 5 in the morning. This is when they do it. First, they will add salt, then they will mix it, then they transfer it into a new pit, or they dig a new hole. Sometimes there is a possibility of discharging or disposing into waters. But this morning it was raised that these people they have to drink strong alcohol. They say that it will stop the smell of the waste. So therefore, in between, during the dislodging, they are taking strong alcohol. And before, their activity is very dangerous, sometimes risky. You see this guy, he was standing on a 3-meter deep pit. He was holding the top part, and there is also a big log which was buried into the bottom of the pit. he might slide. But he was fishing for solid waste that is floating. These people are also involved in waste stabilization ponds because sometimes usually it is very difficult to dislodge with machineries. So therefore these people have to clean or have to remove something that was blocking the flow of the water. As you see here, this guy is in 2-meter deep waste stabilization pond manhole. And here how they are acting. So because of this, they have a lot of problems. Physical life, there is a usual field collapse, bite by owners, or reptiles. They are also exposed to sharp objects. Also, they take alcohol acidity. They are also exposed like hydrogen sulfide, methane, and this poisonous gas. Besides, they don't wash while they are drinking and eating in between, so there is a possibility of bacteriological contamination. And there is also, because of this strong alcohol, not only during the dislodging, they also take it after, in their life, so therefore their life is socially not good. And also they are kind of socially isolated. So from this, also these peoples, manual dislodging peoples are, also there are private investors for truck. Majority of the toilets are dislodged by these pit interiors. So therefore, the lesson where the municipality has to take is to train in hygiene and supply proper tool because they are not using anything, and formalizing the sector. With this, the majority of the solid sludge handling in the tower can be improved. This can be a model for the rest of the towers which are found in the country. Thank you very much.
As you know, we don't have time for questions in these sessions, but if you have a question, could you raise your hand so that Keith can see who he needs to identify in a session? So if you could just, there's one over here as well, Keith. So you know who to look out for in the coffee afterwards. I do apologise, we can't have an open discussion. And you did very well. You said, thank you very much for keeping to time. I appreciate that. Our next presenter is Damien Seal.
Xuống mà làm đi, làm lâu, làm 5-10 phút rồi. Thì em làm máy rồi thôi, để cho anh ăn xong rồi xuống đấy.
His presentation is based on the research that he did as his dissertation. Since leaving the Cranfield, he's worked for Goal in South Sudan and Turkey. Currently with Danish Refugee Council working in Myanmar. So over to you, David. Thank you very much. You can quite use this one.
Right, okay, so I'll get on quickly because we're short of time. Thank you very much. So, firstly, I'm presenting research that took place 2.5 years ago. It was something that was asked for and funded by BUSUP, but done on behalf of Cranfield. And the original concept was to come up with a system of identifying pit emptying equipment. Hello? So when I did the sort of research to begin with, what I found was there wasn't any particular way of determining what was actually inside the pit. So there's lots of research being done into the biological, etc., but not actually how do we determine what's actually inside the pit. So what I did was I took a tool that is used in civil engineering for measuring soil density and I made my own version of it. So basically it was a drop weight cone spectrometer. Hopefully the video will start up. So it's quite simple, 45 centimetre drop with a 2 kilogram weight, so therefore you have a consistent impact each time that you actually drop the weight. quite simply, you measure how much the penetration has gone in each time. So we did the research in Kibera, which is a high-density population in a very small area, and we randomly selected pits across the whole of Kibera. Now, Kibera, the soil is pretty much the same throughout. There's limited impact of groundwater as well. So this is what we expected to find, the more liquid upper part going down to a more dense solid. This is what we actually found. So the petrometer was able to demonstrate that there is a high variety of layers of sludge within a pit latrine. So we had instances, so the top left there is what we expected to find. So quite low resistance to penetration going to a higher resistance. If we look as far as the bottom right there, what we see is we had low resistance followed by high resistance, followed by low resistance, followed by high resistance. So that indicated that there were a number of different hard layers within the pit latrine. And this was shown throughout many of the pit latrines. We had instances where it was ultimately hard on top, going to water below. So this is just an example of one of the pits. So you can see that the pit is actually full, but we took the measurement and we had limited resistance, hard resistance, and then almost no resistance. So what we then did was we emptied it by hand at 1 metre. You can see there we've got quite a loose sludge. Then at about 1.4 metres I was able to take this sample, which was quite a dense sort of honeycomb sludge, and then using the gulper, we were able to basically extract the water from below. So ultimately what we then did was we took the 4 pit emptying technologies that were available in Kibera, which is the municipality truck, the vacuum tug, the gulper, and then the manual. And I went to a number of pits and we actually tried how these would work within each of the densities, pushing the densities as much as we could. So I came up with a gradient, as you can see on the right-hand side there, where we had no impact all the way up to over 300 impacts per metre. And from that I devised a theoretical graph where each equipment for desludging could be put into this graph, and you would know its ability to work against a number of different sludge contents without actually having to add water. So what you see there is that obviously the municipality worked a lot better, it has a lot more force. The vacuum tug was a lot less, and then the gulper very much in line with the vacuum tug. So what we found was that a lot of these would take moisture out, but they wouldn't actually take many of the solids. So the other thing for the actual tool that I ended up using is that a pit emptier can use this to help define what the pit is like before he actually goes in and tries to empty it. So that can come into pricing. If you have no information on your pits whatsoever, again you can go and measure them, and before you put any money into your, spend any money from your pocket, you can help determine what you should or shouldn't actually buy. And I'll leave it there.
If you want to ask Damien a question, please raise your hand and wave so that he can see who you are. As I indicated before, no time to take those questions now, but the idea is you can then approach Damien after the session and you can have your discussion and questions there. So thank you very much, very interesting. Okay, our next presenter, a PhD student, Eugene Apiha Efa, and he's presenting on SAMI Up, Not Smart sanitation project, that's right. And yeah, he's a PhD student at NUS University in Ghana. So, welcome. Thank you very much.
Good afternoon. Welcome back from lunch. I'm presenting on heavy metals, microbial loading, rough gas life for low-income urban areas in Ghana, focusing on Ashanti. My study area is in 3 districts with 6 communities. urban and friendly rural areas. The reason is that the type of sludge that is generated from these areas are different from that are generated from the urban areas. This means that this type of sludge has low moisture content, that is somehow solid in nature, thereby making it very difficult for vacuum tankers and other mechanical inputs to be used to dislodge this type of sludge. The reason is that 85% of the Ghanaian population is being served with on-site sanitation systems. The main ones are the public toilets, which constitute 53%, and also the public toilets are mainly from the KVIP and the pit latrine technologies. This has led to unregulated disposal of fecal sludge, which causes nuisance and serious health impact due to the lack of disposal and treatment facilities in this locality. And this is a picture of the type of toilet found in these areas. The one on the far left is the typical KVIP toilet found in these areas. The one located below the typical pit latrine, which is used by these inhabitants. And this is how the fecal sludge is dislodged manually. And when you look at the pictures, you realize that there is a huge contact from the human interface and with the sludge interface. You also realize that through the sludge, the pit is behind this toilet and the sludge into it. So there is a very serious health implications. So what we do, we need to find out the levels of these microbes and also the heavy metals and see the effect that it has on these manual dislodges. So it led to the determination of the concentration of the heavy metals and also the microbial constituents. Some of the general conclusion from the study was that the levels of the heavy metals and the microbial loads exceeded that is accepted or that is recommended by the EPA Ghana. Comparing that of the rural and the peri-urban, it was realized that the peri-urban sludge had more heavy metals and microbial content as compared to that of the rural areas. We also realized that knowledge from these characteristics would be useful to design a particular treatment facility for this area, as not all treatment facilities are suitable for all areas. For further information, I have posted there, of course, I can detail. Thank you very much.
Yeah, if you want to wave so that Eugene can catch you afterwards, then yeah, Eugene, if you've got a poster like Eugene has, then please indicate that, because then obviously you can go to the poster to find out more information. The abstracts are online now, so there's more information there about the presentations. So yeah, do please contact the presenters and ask them more questions. Right, we now, the next presenter, I should also mention, you may have noticed that the third presentation by James Cush, he's not available to join us today, so we're one short. Next one up is Jamie Radford. Jamie is did civil engineering at the University of Cambridge in the UK, Master of Engineering. He's currently working for Mott MacDonald, a consultancy company based in Cambridge. And this is a piece of research that Mott is doing in partnership with Water for People and the Omni Digester. So Jamie, please come forward. Thank you.
Hi everyone. So the work we've been doing is trying to understand the physical strength of sludge in pits and then the capacity of different pumps to empty them. So, the obvious question, how strong is fecal sludge? We've heard from Damien some examples. And I'm sure you're aware that it's hugely variable. It's not one consistent material. So it ranges from a strong soil on the left-hand urban through to thin, watery septic. And then you've also got the issue of solid waste in the pit. So the first thing that we did was trying to develop some safe simulant materials that replicate this range of strengths, matching shear strength and density to control for pumpability. One of the huge advantages of that is then when you want to test a pump, you know exactly what the material is that you're pumping. Otherwise, when you stick a pump down a pit, you can either pump it or you can't. You stick a different pump down a different pit, and actually you can have a difference of an order of magnitude in strength between two pits next to one another. The other advantage of simulants is health and safety. Inevitably, when you're developing new bits of kit, they don't work too well. And if what you're being covered with is just an inert mix of clay and topsoil rather than fecal sludge, there are obvious benefits of that. So the next step, once we had a safe material to work with, was developing a cheap, simple way of testing strength. So on the left-hand side, you can see a penetrometer that we were using for profiling the pits. That's a research tool that gives a continuous reading with strength all the way, with depth all the way down the pit. But for sort of pragmatic use for pump developers, we needed something a bit easier. So we used the slump test, which is also adapted from civil engineering. Basically, you fill up the metal cone with your material, compacting it down, you pull the cone off, turn it upside down, and measure how far it drops. We calibrated that with a penetrometer, and that gives us a strength chart, basically. So from a very simple reading, you can estimate how strong the material is. And then we also produce some visual guides, just as a bit of a sanity check when you're using it. So going forwards, we developed two simulants, one clay and topsoil mix and one a sanitised sewage sludge mix. We collected a lot of data from the literature, working particularly with UKZN, who shared a lot of unpublished data with us. And this was the sort of summary. So you can see shear strength against density there, and then adding on top of that the simulants. So a couple of key points to note. The maximum strength that anyone's recorded that we know of so far for fecal sludge is around 2,000 Pascal. But all of the machines are maxing out before they get there. Our penetrometer was maxing out, and the rheometers used in the lab are struggling as well. So if you extrapolate that data, which we all know you shouldn't do, you come up to about 10 kPa. So that's why we've been going all the way up to 10,000 with these simulants. And the other thing is density. So looking at the black one, the Milorganite is roughly a lower bound on density, and the coloured ones are different mixes of clay and topsoil, which are slightly higher density. The really wide ranges of fecal sludge are probably due to having inorganics in there, so sand, soil, and things that boost the density up to 2,400. We haven't just been developing these simulants, we've actually been using them in anger. So the work was funded by the Gates Foundation as part of the OmniIngest project. In the middle there you can see a simulant of sort of 40% total solids that was being pumped. We added in 50% debris by mass, and that was done as part of the validation of those machines before they went into domestic field trials, and they actually worked remarkably well. We've also been working with Water People Sani Hub in Uganda. So if you saw Sam Alinga's presentation yesterday, you'll have heard of this already. They're developing improved manual desludging pumps. So on the left there you can see, on the right you can see the left, the Gulper one, and next to it the results from improved testing and development of a Gulper Mark II pump that can pump higher strength sludge and at a higher rate. So for the first time we're starting to get some real quantitative data on what all of these different pumps can do. So to finish up, next steps. Sani Hub are continuing their work. We also have a student at Cambridge who's benchmarking a number of different pumps, so the two Gulpers that are shown here, also the Oxfam diaphragm pump, and the OmniIngest manual pump. So we'll have 4 different pumps in there. We'll also look at things like vertical head lift. So we've got a few other parameters other than just the strength of the sludge. And going forward, we want to use the penetrometer to start understanding pit performance. So understanding pit fill-up rates, why some pits fill in 6 months and others in 6 years. If you repeatedly profile in situ without taking any samples, without emptying the pit, and you can actually start to monitor them over time, look at the hydrogeology and start to try and understand what's going on. And then also in Kolkata in February we're going to test 100 pits with water for people and hopefully roll that out wider and start mapping what different pumps can empty in the different regions. So if you have any questions, do come and find me. I'll be very happy to discuss. Thank you very much.
Thank you very much, Jamie. Excellent, very good. So you've made a note of his email address if you want to contact him or grab him after the end of the session. Okay, we have 2 more presentations. The next one is Tate Roger, MSc at North Carolina State University, a research associate, and he's going to talk to us today about the modified earth auger for removal of variable waste treated and septic tanks. Thank you very much, Tate. Over to you. Choice of mine.
I'll go with this one. Hi everyone, this is Tate Rogers. I'm here with the PR on the project, Dr. Francis Desludging, who's in here. As part of the GC Phase 2, through the funding from the Bill and Melinda Gates Foundation, so I'm going to speed through a lot of slides for you. Most of you already know the motivation for a better pit technology. Current methods are too expensive, they have difficulty accessing the pit, and often they have difficulty emptying the really dense sludge that you find in a lot of these pits. This leads to manual emptying, which, as a lot of people showed already, it's a pretty undignified profession that not many people want to do. So if you're not familiar with the excavator, it's a modified power auger, or more basically a screw that rotates inside of a pipe. As you see on the right figure there, we go up to the pit. There's a hydraulic motor that's powered by an 11 horsepower gasoline engine that rotates the screw and lifts the waste up through the pipe and out into receptacles. This version is version 3 of the prototype. It includes like a dolly frame and a detachable bottom section to make it easily maneuverable to the pit. So Phase 2 has been mainly focused on field testing, and we've been in 3 countries. The first was in Hyderabad, India. The pits we found there, I should mention this was Banka Bailu, the company that collaborated with us. Most of the septic tanks were leach pits. There was really high variability in the sludge, which Jamie can tell you is very common even within the same community. The biggest problem we found is that there was very minimal sludge in the pits that they said before. It was mainly water, and the excavator is more focused on handling the really dense sludge that's found in the pits. Next we went to Durban, South Africa, and worked with UKZN there. In South Africa, we're moving to UDDT toilets, but there's a lot of dry VIPs that are currently still in use that need to be emptied. The biggest issue that you find in Durban, and I'd say these are probably the worst pits in Africa, are trash. As you can see there, there's not much waste in there, it's more trash than anything, so you can imagine the difficulties with putting any kind of pit emptying device in that pit. And which is why in that municipality, manual emptying is a pretty efficient enterprise. These guys are pretty good with their long-handled shovels, but I haven't seen it done yet where there's still not shit around the pit and around the community once they're done. But it's the best option that they currently have. And so the most recent field test we've done is in Mzuzu, Malawi with Mzuzu University. The pits there are difficult to access. So one good thing about South Africa is that the pits were designed so with pit emptying in mind, so the access in the back, but here you either have to go through the hole of the pit, the squat hole, or through the side of the pit drains we did here. They also have significant trash present. You see here we developed a few fishing tools because that's the typical method is to fish out the trash first. So this is one of them pulling out like a big t-shirt, which I always seem to find a pair of underwear in every pit that I've been in. That's pretty typical as well. But once we did get the trash removed, we did have promising results with the excavator. Emptied at around 50 liters per minute until we reached a clog and needed to unclog the excavator. So the biggest issue for us, it works with really dense solids, but you need to get rid of the trash. And it's mainly fibrous materials such as shirts, t-shirts, plastic bags, such as that, which are in a lot of those. So we did have some promising results, so we're sending another unit to Malawi to be tested in parallel. And a lot of that testing is going to be done by Michelle and Mzuzu University. We have a lab set up back in NC State, which we use to simulate waste there. We also have a field set up there, but to test different inlets, so we're trying to figure out ways to handle trash. including just rejecting it or using some kind of shredding macerator tool. We use representative trash that are typically found in pits. And we're also looking at using a vacuum assist, which kind of leads to where we're heading in the future. As most people that work in pit emptying will tell you, there's not one holy grail tool that can empty every pit currently. So you really need a pit emptying toolbox, and that's kind of what we're looking at. We developed a claw and the hook up top, and the claw actually works really well with fishing in Malawi. And so if you need to do manual removal, you can use that. And then we also just bought a open source power unit called the Power Cube 7 that can power all mechanical tools we're using, including the excavator and vacuum system, which is based on the evac by PID, and macerator that we're working on now. And so these can be used to empty either in a multi-step process where you empty the trash first and use a macerator vacuum system, or use simultaneous removal where you're using some combination of vacuum, excavator, or macerator. So we're trying to like be able to handle the entire variability in ways that you find in pits, including the trash. So in summary, the excavator is going to be a pretty effective emptying tool if the trash content can be managed. Like I just said, there needs to be an assortment of tools to empty the pits because they're so highly variable, even in one community from pit to pit. 2 pits 10 feet apart would be completely different. So we have field testing that's continuing right now with 2 units that I mentioned in Malawi, and hopefully we'll be looking for some new field testing locations in the near future. Yeah, thank you.
Just wave if you would like to catch Tate afterward, please. So, one here. I guess if you know each other already, but there's a lot of interesting synergies between the presentations. So I hope you guys are going to get together afterwards as well. So our final presentation, Kumbo Kalulu from the Polytechnic University of Malawi. He's an engineer as well. His research on pit sludge management, pit sludge characteristics in unplanned settlements in Blantyre, Malawi. So please come forward and make your presentation. Thank you very much.
So currently as Polytechnic, we have a group where we are working in a project that's a technical project for southern part of Africa as well as the eastern part of Africa. It's called the Sanitation Research Fund for Africa, funded by the Gates Foundation as well as the Water Research Commission in South Africa. So what I'm going to present is the experience that we had where we created great. It's where we're doing our studies. So what I'm presenting is for planning. That's in the self-planning. So as I've indicated, that is a regional project. Our aim was, in the first place, we want to develop data so that we can compare within the region. That's in Southern Africa as well as in Eastern Africa. So we want to compare with the database that we have. So our most compared to the data we had, we found that the data that we had was based on the different layers. So we can find what are the characteristics of the different layers down the profile of the page. So from that perspective, we had challenge where we had in our sample or access to the page as indicated by the previous speakers through the program that's inside the confined space and not with the packet. So bear in mind that we want to maintain the properties, we don't want to disturb the properties along the profile, and at the same time we are working in this confined space. That was one of the challenges. As we were going through the project, we were excited about the science. Okay, after getting the sample, we go to the lab. But we found from the postcards, we found that the highlight was more than that science itself, but how to be sampled so that we contact the science that were in the first place we were presently. So this was our challenge. Getting the samples, different layers, maintain the properties of the profile, but the different layers do this confined superstructure and move the protocol. Now when we started going to the field, we tried tried to find out what was the practice like, the current practice with those who are involved in Desludging. So the first one of the issues that we found was they are using chlorine. So we felt that if we use this approach, it means microbiological, it means we are able to prepare most, so we'll not be able to establish the microbiological characteristics of our sludge. Another practice is fluorization. So it means fluorization means you're also affecting the profile, exposure to capture along the profile in situ. Then we also have some other practices where there is fishing. So we know that if there is fishing, automatically it means to be that mix of the different layers. So we are capturing the layers, so fishing was the sort of question. Then we have the current that are used to avoid unlike beats for the fear of collapse after Desludging. Chances are very high that will be that collapse. So these people also the current practices that we established from the one group to involve us, our partners. Now in our study we try to be innovative, we try to sample which is more or less working at the second part. But we found that with this, we also not able to sample or get our slide for sample because of the variability that is established from the different bits that we tried this in the field. We also had an issue of accessibility. So we also try using the vacuum pump so that we can sample using the vacuum pump. But accessibility was also another issue that we faced. So this is the pump that is carrying that track. So this track we can access because we are working in opposite fields. The sample that worked for us, we worked in conjunction with an entrepreneur who is called Waste and Environmental Solutions. So for them, they have a vacuum pump on the cat. I think it was presented, one of the presentations, I think Gabriel is presented, they are developing this. So this, because of the size, we are able to access. Now in terms of the sampling, it means we set our pipe and pick the depth that we are going to get the sample. And after that depth, we suck the sludge into the pipe. And after that sucking, make sure that we hold into the pipe, then take out this pipe, and from the mouth of the valve, we draw our sample. So this is the sample that we for us. And we did this in 20 weeks. We didn't have a blind 10 weeks in total. But during the challenge that we faced, we were forced to go to in our work so hard, and we had to plan this where it was in the past access. So in terms of the lesson that we learned, we found that it's easier to work with entrepreneurs who are based. In this case, they are based within our study area, which was planned. So we found that it's better to work with them because it is accessible to both the communities. As for the characteristics of the properties that we established from our lab analysis, I have a poster site, so if there's need, we can meet and I can explain based on the poster that we have. So, thank you for the participation.
Right, thank you very much. As you know, we don't have time to go into an open discussion, but if I could invite those who presented to come forward here, I just let a round of applause for everybody who presented. And I want you to stay here so that if you want to ask a question, do come forward. And if you don't have time now to have a detailed discussion, so all those who presented, can you come forward? If you don't have time to discuss with them now, you can put the card and say, please contact me with a question, or you can send over an email. So, nice big round of applause, please. Just my sort of personal closing remarks is that I am really, really pleased to see these presentations. The reason I'm pleased to see these presentations is that you guys are really leading towards a real challenge affecting the sector, which has been facing us for too long. And having a good understanding of what's in the pit and developing a suite of tools and technologies to actually get the shit out of the pit is absolutely fundamental to vehicle flow management. So my personal congratulations to all of you for the excellent presentation. Thank you. And thank you also for keeping to time. Appreciate that.